Our first presentation is by Peter Duffett-Smith, GM3XJE. We've got the call sign right this time. So Peter is probably best known for people in the amateur radio community as editor for Radcom Plus, which is our online magazine intended to to have more technical articles, etc., and is available free of charge to members. So if you have not had an opportunity at some time to have a look at this magazine, thoroughly encourage you to do so. Just subscribe to it. Peter holds a PhD. Used to teach students physics at quite a high level, but in 2013, the call of Scotland was upon him, and he retired and moved to Scotland. In this morning's presentation, he's going to look at an application that he has for computer modelling of feeders, feed points, etc., so that to have a better understanding of what goes on in the background, why you're not getting the impedance that you might think you have to your feed point, and the software that it has will hopefully demystify part of it. So with that, ladies and gentlemen, I thank you. You please welcome Peter Duffett-Smith.
Thanks very much, Len. Oh, I can hear that the microphone is working. Just raise your hand if you can't hear me. Ha ha. Input impedance of a feeder. I mean, I was asked to talk about this, and I thought somebody was having me on. Well, I mean, how very strange. Then I began to think about it, and I began to realize that I didn't understand why the input impedance of a feeder changes when you change the length of your feeder, when you change the type of feeder, when you change what's connected at the other end. It seemed strange. So I thought, right, okay, well, the best way to find out about things is to give a lecture, and then you jolly well better understand it. So anyway, that's what we're going to be doing. And I hope by the end, you will have a much better view of how things change. So what do we mean by impedance? Well, impedance is always just the current, the voltage divided by the current. As always, the voltage divided by the current. That's it. If it's DC, we can all go home now because it's easy. Voltage divided by current, Ohm's law equals R. But when you're dealing with AC, with radio, then a complication arises because the voltage and the current usually aren't in phase with each other. And in any case, the thing is wiggling around at 10 million times a second. So what do we mean by voltage divided by the current? Well, we can still write that the voltage divided by the current is the impedance. This thing Z is the impedance, and it's the voltage divided by the current. But now we have to have two elements, because we have not only the magnitude, but also something to do with the phase. So we have to have two elements, and what we usually do is to say, okay, well, there's a resistive part, R, and a reactive part, X. And the reactive part is like an inductance or like a capacitance. The resistive part doesn't need any explanation. So that's what it is, R, X. And people who are good at mathematics might write Z is R plus JX, this complex representation. But let's not complicate things. The trouble is that as soon as you start to write equations down and talk about complex mathematics, you know, you can see the eyelids glazing and people wandering off at the back. So I'm not going to do that. I'm going to do everything by a graphical representation. And provided we understand what the diagram means, then it makes it much easier. But there are two things that we need to remember. And that is that the power is only ever absorbed in the R part. This R part, wherever it is, this bit here, the resistive part, that's the only bit which absorbs power on average. The reactive part, which may be like a capacitor, or it may be like an inductor, that does not absorb power. And if you remember that, it unlocks a whole lot of understanding about what's happening. So, as I say, we're going to have a graphical representation. So let's do this. We've got 2 dimensions on this screen. So we will use the 2 dimensions to represent the 2 parts, the resistive part and the reactive part. And actually, we have to go back a bit. We have to start by representing voltages and currents. Again, the voltage and the current, different voltages in different parts of the system, different currents. These may all have phase differences with respect to each other. So here's my graphical representation. People might recognize these as phasors. So here is an arrow, and that represents the voltage V1. This voltage V1, you understand, is actually going at 10 million times a second. It's 10 megahertz. And on this diagram, the phase is represented by a rotation, an angle round. So that if it's going at 10 million times a second, this voltage is actually, this phasor, I should say, is actually going round and round 10 million times a second, which is a bit difficult to show on PowerPoint. So let's just forget about the fact that the whole diagram is rotating 10 million times a second. And we can do this because different parts of the system are all rotating at the same rate, 10 million times a second, or 14 million times a second, or whatever it is. And only the difference in the phase between one voltage and another voltage, all of which are going like this, only the difference in the phase, the difference is important. And here are 2 voltages, this voltage V1. The length of the arrow represents how big it is. The higher the voltage, the bigger the voltage, the greater the amplitude, the longer the length. And here's voltage V2, and this one is of a lower amplitude. But these 2, parallel to each other, are in phase with each other. So here we have representation of 2 voltages in phase with each other. Then we have another diagram here. Here we have 2 voltages, V1 and V2, which have a phase difference. It's about 45 degrees here. And these voltages, V1 and V2, although they're rotating 10 million times a second, they always have the same phase difference. So we just stop the diagram and just represent the phase difference. So here's our graphical representation of voltages and currents. The length is the amplitude, how much, and the rotation is the phase difference in this case. So the next thing, well, in fact, the only other thing that we need to understand is how we combine phasors together, how we combine the voltages together. If you've got this voltage, V1, V2, or whatever it was here, and V1 up here, if you add them together, if you put them into the same place, then what's the corresponding voltage? What's the sum of the 2? And all you need to know is that actually it's just a parallelogram. You get your voltage V1, here it is here, shown dotted, and you get your voltage V2, oh, it's the other way around. That's V1, this is V2. And you put them on the 2 sides of a parallelogram, and the result is just the diagonal of the parallelogram. So that's, in this graphical representation, all we need to know. The length is the amplitude, the rotation is the phase, and adding things together, you just do a parallelogram. So, okay, well, how does this help us? So, what it does, it allows us, it gives us a tool to be able to make a computer program to show how things add together on a feeder. And that's what I've done. So let's see if I can run this thing. Well, right, I'll touch it then in that case. So what I have here, which I think probably I can just expand into the space available. So what I have here is a representation of a feeder. Here it is. This end is the load, the antenna. You can imagine the antenna up in the air. This is your length of coaxial cable or whatever. And here is the transmitter. And we won't be too worried about exactly what's going on here. We can talk about that if we need to. But all this does is to put power at your radio frequency into the end of your feeder. And lo and behold, mysteriously, that power appears at this end and is radiated away, ideally. So in order to understand what's going on, we have to use our phasor representation. And so what I've got here is a phasor representation of the voltage at this point. You see this red bar here, this red bar, wherever it is a representation, shows the point at which you're sampling the voltage. And this is your phasor diagram, and I've started off by having the voltage horizontal on the diagram. It doesn't really matter where you start off, but you've got to make a choice. So horizontal on the diagram here. The length here represents the the amplitude, and it's well, we don't have another one, so it's just along here. Now, what happens when you turn on your transmitter? It launches a wave at 10 megahertz or whatever frequency you're using. It launches a wave which travels along the feeder to the other end. And that wave, if you think about it, when it's all up and running, the voltage here is going to lag behind the voltage here or the voltage here or the voltage here, because what's here left some time earlier than this point. So therefore, as you move along the feeder, so you will see that the voltage, same amplitude, but the voltage changes its phase with respect to the beginning, right up until it gets to the load. So this is the forward voltage, and at this point here, relative to that point there, the phase has changed. It's gone through about 1.6 cycles, in fact. So the other thing I should own up about is that this is a perfect feeder. There's no loss in this feeder. I could put loss in, but it just sort of, it's like having a mist. It just obscures things. So it's a perfect feeder. So the voltage of the forward wave when you get to here is the same as the voltage of the forward wave that you started with. It's just the phase that's changed. Now what happens here? Well, what happens here depends upon the load. And I can change the load. Here, I've got it written down here. I've got the resistive part and the reactive part. And I've made it a short circuit, load of 0 resistance and a reactance of 0 ohms. Okay, so what happens? Well, the power in the wave can't go anywhere. There's nothing to be absorbed in. Remember I said that the resistive part is the part which absorbs the power. Well, there isn't any resistive part. It's a short circuit. And there isn't any reactive part. In any case, that wouldn't matter because that doesn't absorb power. So that power can't go anywhere. And in fact, what happens is that it bounces off. You know, it's like throwing a ball at the wall. It just bounces back, can't go anywhere. So a reflected wave is set up at this point. And furthermore, because of this particular circumstance where I've got a short circuit, the reflected wave must be such that the total voltage at this point is 0. If we didn't have a 0 voltage, but we had a short circuit, we'd have an infinite current, and that can't happen. So the voltage actually just changes phase, the voltage, I should say, of the reverse. And if I try very hard, what do I have to do? Okay, there we are. So this now represents, this purple line represents the phasor of the reflected wave. So you've got the red line, which is the phasor representing the forward wave, the voltage thereof, and the purple is, that's purple-ish, is the phasor representing the voltage of the reflected wave. And at this point, they must be equal and opposite, because they must add up to 0, as otherwise you'd have an infinite current, because I've got a short circuit. I mean, it'll change if we change this impedance. And of course, as you go back down the line, so the phase of this one changes with respect to this point and winds in the opposite direction, because that's how the phase is changing. So as we go back down the line, you can see that we've got these two phasors representing these two voltages, the forward wave and the reflected wave. And when we get back to here, the forward wave is, well, that's where we started, so it's along the horizontal. The reflected wave has gone to here, so it's a phase difference with respect to the forward wave. And we can actually add these together using the parallelogram rule, but fortunately we don't have to think about it in those terms. We can just let the computer work it all out. So starting from here, the resultant in the middle here, in green, this little green thing represents the result of adding the forward wave and the reflected wave at any point. And as I say, right at the end, let me just get this to right at the end. Right at the end, the forward wave and the reflected wave are equal and opposite, and you get 0. But as you go down the line, that's no longer the case. One is winding one way and one is winding the other way. So there'll be a point where they're actually adding together and you get twice as much. And then another point where they exactly cancel and you'll get 0. So you get, as you go down the line, the resultant, which is the green, getting bigger and smaller, like this. Now we can plot that as a familiar SWR plot along the bottom. So here we have in green the resultant. This is the voltage. At the beginning, at the end, at the load, because we've got a short circuit, the voltage is 0. But come down the line just a short way, to here in fact, and here now the phases of the two, the forward wave and reflected wave, are now exactly the same. And so they add together and give you twice as much. So if that's 10 volts, then this will be 20 volts at this point here. And then go down a bit further, and hey, they're exactly equal and opposite here, and so you get 0, and so forth. So you get this familiar standing wave pattern, in this case the voltage, so this is the voltage standing wave pattern, and we measure that in terms of the voltage standing wave ratio, the VSWR. Don't suppose you can read that, but it says VSWR, and all that is the ratio of the maximum to the minimum. So if you can imagine that's 2 and that's 0, when you divide 2 by 0, you get something very large indeed. Computer can't handle it, so it just says large. But of course, that standing wave ratio will change depending upon the load that you have. Supposing I was to put, I don't know, 20 ohms in there, so let's put 20 ohms. So now what we have is a partial absorption of the power in the resistive element of the load. It's only a partial absorption. It gives rise to a standing wave ratio of 2.5 to 1. So that's the ratio of the biggest bit to the smallest bit. Measure that bit, divide by that bit, and you get 2.5. And you can see that you are now transmitting something in your 20 ohm antenna. I was going to say the radiation resistance. Well, it's some of various things, but that's going on there. And so the amount that's actually reflected is smaller. So the amplitude of the reflected wave is reduced. Here's the forward wave. It's still the same length, but the reflected wave, it's reduced. And that means that it's not perfect reinforcement and it's not perfect cancellation. And so you get this wiggly line, which is familiar to us all. And we have, I have assumed a 50 ohm characteristic impedance for the line. So if I terminate with a 50 ohm resistive load, then all of the incoming power, all of the forward wave is absorbed. It all goes into the antenna. Nothing is reflected. You see the reflected wave has gone to 0. It doesn't matter where I am. That is always 0. And the sum is always just then the same as the forward wave. And the line is then flat. And that's the perfect condition. Remember, this is a perfect line. In reality, it isn't quite like this, but it's a good approximation at HF using high quality feeder. So now then the same thing happens, of course, to the current. We have the voltage having a phasor representation which winds like this. We could equally well represent the current. So this is now the current. So the current is in blue, the sum is still in green, and the reflected current is in a different color, and I can't remember what it is, but let's we can get to that. If I put 0 back in here. Oh, all right then. Okay. So just to pass that by. Let's put in 25 ohms there, shall we? Okay, there we are. So it's blue. It's a light blue phasor representing the reflected current. So you have these two waves. You have the voltage wave and you have the current wave. And both change phase as they advance and are reflected. Now what you get then at the input depends upon the way the voltage and the current have added up at that point. Because remember I said that the voltage divided by the current is the impedance. So the voltage divided by the current at this point depends upon the sum of the current and the sum of the voltage at that point. Let's go back down to there, that point there. So at this point, the sum of the voltage of the current, we're doing current, the sum of the current is here with this phase and this amplitude. And if we go back onto voltage, then let's get there, right there. Then the sum of the voltages, the forward and reflected wave, is like this. So different amplitude, different phase. And if we just compare those two, see if I can persuade it to stay there. Right, there we go. Oops, no. It's quite hard. Okay, here we are. So the green there is the voltage, is the current, the voltage at this point. And the current is like that. The green now represents the current at that point. And you can see that the voltage and the current are not in phase with each other. but the impedance is just V divided by I. Now, I'm not going to go into the intricacies of how you do a division on this phasor diagram. It's a pain, but what I can do is to point out one or two interesting things. The first thing is that obviously the ratio of the amplitudes and the phases at this point depends upon how much reflected stuff there was. So therefore it depends upon what your load is. Change the load, you're going to change the ratio, you're going to change therefore the impedance at the beginning. Secondly, it depends on how many wiggles you've got in your VSWR plot. I've got a length of 1.6 here. If I change that, say, to, I don't know, 1.7, well, you can see it's changed. It's changed because your wiggles, which have to fit exactly into your length, have added up in a different way here. So the impedance at the beginning is going to depend upon the physical length, or actually what matters is the number of wavelengths actually in the cable, and you have to take account of the velocity factor of the cable for that. Now we can play a few games here. One is, let's see what happens if we have, say, a purely reactive load. Let's have a 50 ohm reactive load with the resistive part equal to 0. Last time I said 0, it said, oh no, it's all right, okay. Now we know that that must give you an infinite VSWR, because if this is entirely reactive, there can be no power absorption. So whatever its value, the impedance, the power will always be reflected. And the impedance down here will always be entirely reactive. And you can see it is. The input impedance, this calculates what it is, 0, and actually 98.1 ohms. And it doesn't matter what you do, you can try changing this, say, to minus 100. How about that? A capacitive reactance. Well, it doesn't matter. If there is no resistive part, there's no power absorbed, and the input impedance will always be entirely reactive. And here it is, input impedance of 0, and now we've got a reactance of plus 7.5 ohms. And that's just simply because of the way the things react together. Now there are various other things we can do. We can have part resistive and part inductive, or capacitive in this case. So let's put a let's put a 50 ohm resistive part, but you've got a 100 ohm reactive part. You can see that even though your resistance is now exactly right, you are not absorbing all the power. You've got you've got a 5.83 to 1 standing wave ratio, and the input impedance, well, actually the resistance has changed to 8.6 ohms here, and 3.8 ohms of reactance. Now, if you've got an ATU here, you can tune out this bit, and if your ATU is good enough, you can change that to look like whatever it is that your, usually 50 ohms, that your transmitter is expecting. And then, even though you have this standing wave on the line, all of the power that you put in that end will be dissipated in the 50 ohms, because this bit's been cancelled out by your ATU, and the impedance has been changed by the transformative property of the ATU. There are some other interesting things. We could, for example, change the length of the cable to, say, a quarter wavelength, 0.25. That makes it quite a short cable in this case, so you've got small wiggles. But look what happens if we have a purely resistive load. So we'll put 0 in there, and we will say make this 100 ohms. then in that case, you've got a 50 ohm cable, you've got 100 ohms at this end, the input impedance is 25. It's a nice round number. And guess what? 25 times 100 is 2,500, and the square root of 2,500 is 50. So there's a clue. This is now a quarter wave transformer, and if you take the impedance seen at one end and multiply it by the impedance seen at the other end, this is only when they're resistive, and it's a quarter wave long, then the product of those two is the square of the impedance of the cable. And that's true not just for quarter wave, but it's true for 3/4 of a wave or 5/4 of a wave. I mean, we can change this to be any odd number of quarters of a wave. So why don't we put in 9/4? What is that? 9/4. I can't do that in my head. Thank you. Somebody said the answer. Thank you. 2.25, I think. Is that right? So there we are. So now it's exactly the same. 100 times 25 is 50 squared. One other thing just to show you, I think, is how you might do all of this in practice. Well, in practice, of course, we're radio amateurs. We suck it and see, don't we? We string it up and we twiddle our knobs. Hey, it works. But if you did want to calculate, formally what the impedance at this end was when you had a line of a certain length and an impedance at this end of a certain value, you can do that very simply by running a spreadsheet. And I have provided two spreadsheets here, and these are spreadsheets. So here's one. Simply bung in your feeder, 50 ohms. It'll deal with absorption. It'll deal with the attenuation, I should say. So I've got 0.1 of a dB per 10 meters, and I've got 4.5 meters in length, and I've got a velocity factor of 0.8, and I'm operating at 21.2 megahertz, and that's my input, and here is the impedance that I get. A series resistance of 13.3 ohms, and a series reactance, like an inductor, of 47.3 ohms. And you can do it that way around. By the way, if anybody wants this, I'd be happy to provide that to them. If you've got a memory stick in your pocket, I'll load it down for you. You can do it the other way around, and you can say, okay, well, in this case, I actually measure an impedance at the transmitter end, because my antenna is 50 feet in the air. I actually measure an impedance of, in this case, 13.27 ohms with a series reactance of 0.36 of a microhenry. Then this will tell me what the impedance of my antenna is. So my antenna has actually got 165 ohms and 183 or 184 ohms. So that's a useful tool if you want to do it formally. Most of us don't. We suck it and see. So that's it, really. I expect there might be one or two questions. Here are some articles that I have written about all of this, and those two spreadsheets are actually provided, discussed, demonstrated in this particular article here. Okay, that's it, I think.
Thanks very much. It's actually quite scary to think back about 55 years or thereabout when it was college, and they say it was power engineering I did, and the principles are exactly the same. A power line's a transmission line, exactly the same. If my lecturer could give me that presentation, life would have been an awful lot easier for me. So thank you very much for that. It's a very good rest. Are there any questions? Just give us a second to get to the back.
Hello, thank you for that presentation. That was so insightful to see it visually. So I actually have two questions. One is, what software were you using to show it?
So I wrote this in our Pascal, free Pascal, under, it's called Lazarus. It's all free, which is why I'm using it.
So you wrote the software yourself?
Oh, yes.
Oh, are you sharing it so we can give it a go?
You can talk to me about that afterwards.
Okay, I will. And the other question is, when you showed the signal being reflected,
Yes.
I don't know if I got it wrong, but it looked like the frequency of the reflection was different to the frequency of the signal that was going in.
No, you got it wrong.
Okay.
The frequency is exactly the same. If you've got a system and you bung in 10 megahertz, you'd be extremely surprised if something else was going at 11 megahertz.
Okay.
Unless you had a frequency changer.
Any other questions?
Yeah, good morning. I just wanted to pick you up on, you said right at the very beginning that power is only absorbed in the resistance.
Yes.
Then you went on to say, forgive me saying, that you start with the transmitter bugging power into the coax.
Yes.
It's always a confusion when people say that.
It's insightful. That's a very good question.
Yeah.
So
Sorry.
what one has to remember is that when we're talking about these things, we're always talking about the steady state condition. When you start, then there is a time before the steady state condition is reached. It will be microseconds, but nevertheless there will be a time. And clearly, at any point, if you are feeding 50 watts into your cable, that 50 watts is starting from here and going to there. Then while it's traveling, that is stored in the cable. And it's in the cable as combination of magnetic and electric field. So so it's true that the power, the cable itself, has to reach the steady state condition by getting some power, getting some energy into it. However, the characteristic impedance of the cable is real. It's a resistance, and you can. It's a peculiar resistance in that it doesn't actually absorb any power in the steady state, and the reasons for this are quite subtle, and it is a confusing point. I was confused by this for years actually, till I
must admit, I use, because I don't really know what I'm talking about, I use the word energy. I say you feed energy into the cable, then you're not confused with absorption of power.
Yeah, you can use energy. I mean, one is the rate of the other, so, you know.
Thank you. Thank you very much, Peter. That was very good. The question is, where should you put the ATU?
Oh, that's very easy. You always put the ATU at the transmitter end. So actually, I think your questions are quite subtle. It really doesn't matter. You can put the ATU wherever you like in the system that I've described, which has a perfect feeder. You could put it in the middle, or you could put it up in the air, provided you adjusted it so that there was 50 ohms at the transmitter end. Then you're done. But it's easy. It's easier. It's easiest to have it actually by the transmitter.
Indeed it is. But at that point, the SWR on the cable is not one-to-one.
It could be. It
something.
Could be. It's something. And it doesn't matter. If you are feeding in 50 watts, I'm using 50 too much. If you're feeding in 10 watts, that 10 watts must be dissipated somewhere. Well, where is it dissipated? If you have a perfect feeder, then it's not dissipated in the feeder. Even though you've got a high SWR, doesn't matter. It's dissipated in the resistive part of the load. And if the resistive part of the load is just, which it never is just the radiation resistance, you're doing as well as you could possibly do. Now in practice, of course, it's a lossy feeder, so you have the feeder gets warm, you get some loss in the feeder, and in that condition, a lower SWR is better, because you actually don't want this power sloshing around, and every time it sloshes, you get a bit more loss. But otherwise, doesn't matter.
Any other questions?
Yeah, good morning.
Money.
Your whole discussion has been about transmitting.
Yes.
Can we talk a little bit about how your receiver sees a situation? In the case of the perfect feeder, okay, fine, but you have now a reactive antenna with both real and imaginary parts, and how does the feeder look at that? And is in fact your receiver a 50 ohm match in most cases? I guess it probably isn't, but I'm not sure about that.
No, you guess wrong. It is. There is this wonderful theorem. Well, it's called various things. I like to call it reciprocity. If you've tuned up everything correctly for transmission, then everything is tuned up correctly for reception. So if you see, if you have tuned your ATU so that it provides a 50 ohm match to your transmitter, then your receiver will also see the 50 ohm match. The receiver is looking directly at the feeder. So you can't have, well, it seems to me you can't have one impedance being different from the other, and in fact it isn't. So don't worry, tune it up on transmission and then you're all right.
I'm not sure you're correct in this saying that your receiver has a 50 ohm input impedance.
It doesn't matter really what the receiver input impedance is. If it's been if it has been manufactured in order to work best with a 50 ohm impedance, then it might have an input impedance of 5 mega ohms or something. But if it works best with 50 ohms and you have tuned your ATU to give you 50 ohms, then it's all right. Oh, I know, you want to discuss this, don't you? Yes.
Any other questions?
Yeah, one more.
Oh, where are you? There we are.
Hello there. I just want to talk about velocity factor
Yes.
of different feeders.
Yes.
Now, basically, is that almost like a speedo, could
Yes.
we say, right, for
It's
the RF?
exactly that. The velocity factor of radio waves in free space is 1, because it is the velocity of the waves divided by the velocity of the waves in free space. If you put radio waves through a medium, they always go more slowly. It's still at 10 megahertz, but they actually travel more slowly. And then the velocity factor, which is the velocity in the medium divided by the velocity in free space, is 0.9 or 0.95 or something. In the case of a cable, if it's an open wire cable, so there is no dielectric or not much dielectric, then the velocity factor is 0.9, 0.95, really quite high. In other words, the waves are going nearly as fast as they would be in free space. But most of us use coax, and coax has a solid, well, unless you're using a special coax with holes in, but anyway, it has a solid dielectric, and this slows things down typically to about 0.8. And it's also lossy, by the way. It's where the loss in the cable comes from, the attenuation.
I've got that.
Okay, any more questions? Well, thank you for that, Peter. I must admit, I really enjoyed that. It took me back a bit. But as I say very well, I think that you've raised some issues that Lisa, Bob, etc. will take offline and have a wee chat with you. With that, I'd like to ask you to thank Peter for his presentations in the usual way.
Thank you very much.